This is a lesson on the second law of thermodynamics in the heat and thermodynamics unit. In the realm of second laws, this is a pretty big contender for importance in regard to conceptually grounding some of the observations and applications that we have for thermodynamics. To conceptually highlight what I've covered in thermodynamics so far, you've seen that energy is conserved at all times and can be specified in certain ways. Physicists will divide this into different ways, and we've been focusing on thermal energy and also looking at work done. We're interested in the states of processes, not the mechanisms or substances of the processes. And this framing, when you think about it being independent of the mechanism, independent of the substance, then you can focus on how the applications encapsulate the concept of the second law in application. The first law quantifies this concept that energy is conserved at all times. We have a change in thermal internal energy, and that comes about because of heat and work being done by the system in question. What you've seen is that no other law specifies the natural direction of energy transfer. This is not a directionality equation. This is just an equation. It says two things are equal. It does not have arrows in it in any direction, right? Energy is a scalar. We've seen the zeroth law, the law of thermal equilibrium, defining what thermal equilibrium is, and that's no heat transfer between two objects in contact. The third law was the law of absolute zero or zero entropy, where there's always motion and there is always disorder. The third law is of absolute zero or zero entropy, where there is always motion or there is always disorder. These are things that we know are true in the cosmos, but they don't touch on why things are spontaneous, why natural processes proceed in one direction. Energy flow has rules about it. I wanted to cover some terminology before I move further in the direction of the second law in regard to statistical mechanics. The second law talks about disorder, and so when we think about the second law, we have the terminology macrostate, microstate. We have systems, a closed system, an open system, but microstates and macrostates are important when considering disorder. A macrostate focuses on the parameters characterizing the state of the system as a whole, whereas a microstate focuses on the parameters characterizing the processes happening at a microscopic level. Okay, so let's just look at a really simple example, and this just comes from statistics and probability. The difference between a microstate and a macrostate can be seen by flipping three coins. So the macrostate is like the larger thing that's happening. And when you think about three coins and there's heads and tails, you can have a situation where there's three heads. You can have a situation where there's two heads. You can have a situation where there's one head. And you can have a situation which is zero heads, which is all tails. Okay? I haven't specified in what order those are in. I've specified the larger state of a throw. If I throw three coins, you could end up with three heads, two heads, one head, or zero heads. But if you flip them and lay them out, you can have different orders. And so three heads, that happens in just one way. Two heads can happen in a couple of different ways. I can have heads, heads, tails. I can have heads, tails, heads, and I can have tails, heads, heads. All of those have two heads and one tail, and so there's three different ways that can happen. Similarly, for one head, I could have head, tails, tails. I can have tails, heads, tails, and I can have tails, tails, head. And so you can see that head move across, and I have two tails in all the places. The last option here is zero heads, which means three tails. Overall, when I count all of these up, I end up with 8 different microstates. There's 8 microstates. But overall, there's only 4 macrostates. So that's the idea of the difference between a macrostate and a microstate. What's the larger sort of what's possible, and then the microstate really looks at the details of how each of those arrangements happen within the larger macrostate. So let's change the example and increase n value. Here I had 8 options for microstates. Arrangement of air particles in a room. Think about the room you're sitting in and all of the air particles in it, and think about the arrangement of all those air particles. A classic example is they could all be on the right half of the room or on the left half of the room. That's not a likely thing to happen, but it is a microstate that's available to the air particles in your room. So the second law looks at when a process happens, why do we not see all of the air particles on the left half of the room or the right half of the room? Why does that not happen? So here's the larger idea of the second law of thermodynamics, and I am going to point out the picture on the right here, which I borrowed from OpenStax College Physics, page 626. What you can see is that we have a hot reservoir. This is what we call a hot reservoir at a temperature a hot temperature. We have heat. This is conceptualized as heat. And down here we have a cold reservoir at a cold temperature. And this is basically the second law in art form, is it's just heat will flow from hot to cold. There's different ways to conceptualize this, though, and that's why there's a lot of words on this slide, and I'm going to walk us through it. Heat flows spontaneously from a substance at a higher temperature to a substance at a lower temperature and does not flow spontaneously in the reverse direction. And remember, temperature is a measure of random motion. And what I want to point out here is that we're looking at random motion, random energy transfer, just random collisions in here, right? These things are moving around fast. They're going to transfer energy to the slower moving objects. And this is a random process. It's a spontaneous process that happens. And it will always flow in this direction. A corollary of this, sort of the reverse, this is also true. No spontaneous process exists which results in net heat transfer from cooler to hotter objects. All right. So the energy in the cold will not spontaneously just flow to the hot. This sounds intuitive to you, I'm sure. This is how you experience the world, is heat flows from hot to cold. You're familiar with that. But this is not the only implication. This is one way that this second law manifests in the cosmos. So let's look at a few others. There is an increase in disorder for any system undergoing an irreversible process. So when we think about the system, when there's a lot of fast-moving hot particles here and a lot of slow-moving cold particles here, that is an unlikely state for the system, just like all of the air particles being in the left half of the room. I'm not saying that this is not likely to happen. Obviously, we have this separation. But when energy flows, it will flow from one place to the other. And we're thinking about this in terms of disorder, right? Random motion, the disorder, this likelihood to a number of states. And the more states, the more disorder, okay? The total disorder of a system either increases or remains constant in any process. It never decreases. So when we quantify and count disorder in a system, we have a rule that we know this disorder has to follow. The last part here says, when a system is composed of a large number of particles, the system is exceedingly likely to spontaneously move towards the thermodynamic macrostate that corresponds to the largest possible number of particle arrangements in their microstates. So I've been hinting at this. This is why I brought up the terminology, and we're thinking about this idea of what are the possible places, configurations of a system, and what is the likely ones and what are the unlikely ones. And so again, this is probability, this is statistics, this is your introduction to statistical mechanics. And notice that we are just a few steps away from quantum mechanics, which also has probability involved. I wanted to cover some important notes for the second law, and here's the second law here. I just put it up here, this last more formal one that talks about the micro and macro states. What we're assuming in that situation is there's a large number of particles. The example I gave you to talk about microstates and macrostates was a small system, but the next example I gave is a very small example of the number of air particles in the room. Okay, we're assuming a huge number of particles. The law is emphasized as a law of probability or likelihood of a macrostate, and you've heard me talk about that. These are terms that I have not mentioned very much before this point, and now here they are because they are a fundamental part of the law. There's certain things in the cosmos that scientists cannot predict. There is a probability distribution which they can rely on for observations, but they cannot say what will happen next. So, this law is about incoherent random motion in the spontaneous direction. Again, note that we're incoherent, we're random, and there's spontaneous things going on, things that we can't control that just happen naturally without our interference. Because there is this level of probability, this law does not specify the microscopic arrangements, only that the system tend toward the largest number available to the particles. It will always tend that direction. So let's think about applications of the second law. Here's the second law as I introduced it, and what applications do is they recognize that the heat leaving the hot reservoir, which I will call QH for hot heat, can be divided up, right? Here it is, it goes, and so it does it naturally. So what we can do in an application is take this thing that's naturally happening and take some of it off and encapsulate, or what we call extract, work from the process that's naturally happening. This is what we call a heat engine, and what we really want to do is maximize the work out of a spontaneous process. How we quantify this is just saying that the energy in, which is just the heat in from the hot reservoir, has to equal the work that is extracted plus the heat that was left over and was going to the cold reservoir anyway. This is a very common sense accounting of all of this energy. So that will be our focus of applications in the next lesson.